In this chapter, we're going to start taking a look at the first of our three types of numerical methods with respect to calculus. We're going to start with numerical differentiation, and then we're going to subsequently look at numerical integration and numerical methods for differential equations. Just a kind of idea as to what numerical differentiation is. Let's say we have a continuous function. Let's define it as f of x, and let's have our function look something like this. All right, so we have a continuous function, looks like that. All right, and let's say that we're interested in the derivative at this point. Now we know that to be able to, the slope really represents what the derivative is, or the derivative represents what the slope is, vice versa. And so we know that usually what we do is if this is the point A, then for us to be able to find the slope, that would be f prime at A. And a lot of functions, it's not too bad for, okay? But there are some functions where differentiation is fairly difficult and rather monotonous, or the function is just really difficult for us to try to work with in the beginning, right? And so what we might want to do is we might want to approximate what the slope is at that point, all right? So now, of course, one of the things that we might have done in Calculus 1 was we found, and I know that's not exactly tangent, but just imagine that's a tangent line. And what we might have done was tried to figure out what the slope is using another point just off of that tangent line to kind of represent what the slope might be at a point fairly close to the tangent, all right? And that's sort of what we're going to be doing, is that being able to use other methods to be able to find what the derivative of a function is at a point approximately. All right, so that's kind of an overview as to what our numerical differentiation is going to be. Now for us, we're going to be taking a look at various methods of numerical differentiation. And one of them, in fact, one of the more common ones, is by utilizing our Taylor series, all right? And so what I'm going to do is I'm just going to illustrate the derivation of one of the formulas, one of the most fundamental formulas for approximating a derivative using a Taylor series. So from Calculus 2, okay, you might remember seeing a Taylor series that's expanded about a specific point A. All right, so maybe I want to go ahead and approximate a transcendental function or just a not so nice algebraic function using a polynomial, and I get a Taylor polynomial. All right, and for us to truly get a really, really, really good approximation, okay, then we'd have to go out to infinity. In fact, as it goes to infinity, we actually almost get what that function is, but we know that we can't reach it. So let's say for some reason that we wanted to go through and approximate the derivative, or just not even the derivative yet, but some value on the function. I'm going to call that x sub I. And what I could do is I could use a second order Taylor polynomial or second order Taylor series. And so what I would do is I would just plug in 0, 1, and 2. And this is what it would look like. Okay, so I'm going to say fx sub I plus 1, which is going to be the next value on the Taylor polynomial, is going to be equal to, so this would be the 0th derivative at the point x sub I. So I'm just using the original point x sub I to predict the next point x sub I plus 1, plus the first derivative over 1 factorial at x sub I. So just imagine a is x sub I at this point. And then plus the second derivative divided by 2 factorial. So we're just increasing n, and we could keep doing that forever. Now, let's just assume that anything after the second derivative is going to be an error, all right? Because that's basically going to be, if we were just using a linear or a first order polynomial to represent it, then everything after this would be the difference between the approximated and the exact value. So let's just truncate all of this stuff in red. Then this is what we're going to be left with, all right? Let's let h be the step size. In other words, the difference between x sub I plus 1 and x sub I, right? What we could do is we go through and solve for the derivative, and then we get this formula. This is called a forward difference formula, okay? So the next I, in other words, if we just add whatever x is plus the step size minus fxi divided by h is going to be equal to our derivative at f sub x sub I, right? So, and this is geometrically what's going on right here. So this is our point fx sub I, and we'd like to be able, if at all possible, to find the slope at that point, right? So really what we're looking for is we're looking for, and again, I know it's not a good picture of it, but we're looking for the slope there. And so what we do is we just pick another point, fx sub I plus 1, right? And instead of using the secant line, we just go through and we try to find the Taylor polynomial approximation of that, all right? So centered about that point where x sub I is just going to be your a and your Taylor polynomial, all right? So that's our forward difference formula. So we're going to hold on to this. Now, what if we wanted to take something and use a backwards difference? So in other words, instead of using the next x, we could use the previous x. So maybe right here might be fx sub I minus 1, the previous point, all right? And we would go through the exact same steps as we just did above, okay? So we'd expand the Taylor polynomial, except it would be x sub I minus x sub I minus 1 right here. All right, so that would literally be about the only difference that we're using with this. Well, we could go through and we could get a backward difference formula, all right? And notice that it looks almost identical to the forward difference, except now we're just using a previous step, all right? So we'd have f sub I minus fx sub I minus 1 divided by h, all right, instead of the forward difference, right? A better estimate most times is if you'd average these two, all right? So if I was to just add these together and divide by 2, now notice if I added these together that these would cancel out. And then if I divided by 2, I would just basically get minus f sub x sub I minus 1, and then positive f sub x sub I minus 1 divided by 2, all right? So this would be our centered difference, right? And what we're going to do at first with MATLAB is we're going to explore if we take a function, we numerically try to find the derivative at different step sizes h, using all three methods, the backward difference, the forward difference, and the centered difference. And then we find the actual value of the derivative at that point, and then we just find the percent differences. So in other words, we're just basically comparing and contrasting which of these are better or worse, if there really is a significant difference, and what happens as we change the step size. And of course, we'd like to try to keep the step size small, all right? So a lot of times we use like h is equal to 0.1 or h is equal to 0.01, etc. We don't want a big step size because the larger the step size is, the larger the error that we're going to get is. All right, so we'll take a look at an example of how to program this in MATLAB in our next video.